Okay, moving along here. Intersection of a line and a plane. So now we're looking at the interaction, how a line intersects with a plane, and now you get to do there's a bit of thinking involved here, moving out of that knowledge and understanding. So today's goal, I can determine the solution or solutions to the interaction between a line and a plane, and then describe my results through words or pictures. So it's very important that you can articulate your answer. So there are three possible cases for a line and a plane. So the first one that we're looking at here is if they intersect. So if they intersect. So make sure I have lots of room here. So what happens, using a diagram here, if this is my plane and we have a line passing through the plane at a point, which would look like that. So our intersection point's right there. Before we go through and actually do the process, there's a series of checks that we can do to save us a little bit of time. We know that the normal to this plane is perpendicular to it. If the line, and maybe I'll come back actually, it might be easier to see a situation where this is true. So if we look at the second case, if the line is, let's say, on the plane, okay, so we have a point here. Here we would have a point. Here we have on plane, which we call coincident. Coincident. Okay, and this is where the check will make a little bit more sense. So again, I said the normal is perpendicular to the plane. So if we know the normal for the plane, and we know the direction vector for the line, if they are perpendicular to each other, so if it's on the plane, and we took the dot product of the direction vector and normal, we would get a zero value. If we did this same thing for the previous or the first example when there's a point, since the line is not on the plane and never will be if it's going to pass through at a point, it will never ever equal zero. So if we do this check right off the start and you find that the dot product's not equal to zero, you know you're going to have a single solution. So you're going to have an independent system where you'll be able to find a value. So this is an independent system. What happens when this is true, the check? Well, if I go to my third case, we're going to find that we're going to have to extend the check out one more level. So the third case is what happens if the line that we're interested in and the plane are parallel to each other. Because if they're parallel to each other, the normal and the direction vector are still going to be perpendicular. Still parallel to plane. So if we did the check here, that same check, and we took the dot product of the direction vector and the normal, we're going to find it's also zero. So how do you tell the difference between the two? The second part then to the check, if we use the line's reference point, and plug it in to the plane equation, so what's going to happen then, our second step then, so to speak, I'm going to cheat like crazy here. What's going to happen, I guess if you want to think of this as step one, here's step two. You plug it into the standard equation of the plane that's given. You're going to do a left side, right side check, and what you're going to find is if left side equals right side, and I got an example of this, then we have a situation where the plane and line are coincident, which means you have a dependent system. And in this case, we'll find left side is not equal to right side, so we have an inconsistent system, which means there'll be no solution, which makes sense because the line and plane never touch. All right, so there are the 3 checks. And you want to do the check before you go through and do the algebra because it speeds up the process significantly in the homework. And it also allows you to be more comfortable when we get to different types of interactions as they come. So I've already got that done, so you had space for that below. And finding the intersection between the following lines and planes. So I've got 2 examples here to run through, and we want to find out what we're dealing with. So before I look at this, I have a line in vector form. So this is my line in vector form, and here's my plane. Only planes can be standard form, and we know it's a plane because there's a z component. So my check, I'm going to start with it off to the side here. I'm going to take the direction vector and dot it with the normal and find out what that's going to give me. Direction vector is 4, 3, 2. The normal would be 1, -1, -2 from the plane. So I get 4 minus 3 minus 4. And I know that 4 take away 4 is 0, so I really don't care what the actual value is other than the fact it's not 0. So therefore, they intersect at a point. So there we go. So there's the check done. I know this actually works out to be a point. So here's your process. We need to write the line in parametric form. That's step 1. So we end up with our line is actually equal to x equals 3 plus 4t, y equals 2 plus 3t, and z equals -1 plus 2t. Step 2, substitute the line equation into the plane equation. I always like planes and lines when they interact because it's the easier of the ones to work with. So I know from above the equation is x minus y minus 2z equals 0. So I just substitute the parametric form in. So 3 plus 4t minus, I recommend the brackets because it reminds you to distribute the negatives through, minus 2 times t equals 0. So what happens when we look at what we have one equation with one unknown. So it's just a matter of simplifying, collecting like terms, and solving for our value of t. So collecting my t's together, 4, 1, -3. And my numbers, 3. That gives me a 1. That gives me a 3. To the other side. So I find t equals 1. Now remember, we're looking for a point. So to finish this off, if t equals 1, using that parametric equation from above, so line 1, x equals 3 plus 4t, y equals 2 plus 3t, z equals -1 plus 2t. We get the coordinate, and just substituting 1 in for t, we get 7, 5, and 1. So there is our final answer. The line and plane will intersect at 7, 5, 1. And that's the process, steps 1 and 2, that's the process that we use for all line and plane interactions. Okay, the next example. Again, you always want to start with the check. So what do I have here? I have a line in 3 space because you cannot have a plane in symmetric form. And here's my plane. And this was my line. So my check, I want to do the normal dot the direction vector. So the normal, taking that from the plane, would be 5, 1, -2. And my direction vector would be 3, 1, and 8. So I end up with 15 plus 1 minus 16 equals 0. So now I take my, because this is equal to 0. It's either parallel or coincident. So using the reference point, and I'll just call it point A. So this is coming from the symmetric equation. It would be 2, negative 5, 6. We do a left side, right side check for the equation of the plane. So the left side is equal to 5x plus y minus 2z. Right side is equal to 0. If I was doing this in class, I'd take the right side. You guys can work on the left, but I'll help you out here. Times 2. My y value is negative 5, and 2 times the z value. So we have 10, take away 5, take away 12. And when we do that, we end up with negative 7. So therefore, left side is not equal to right side. So if that's the case, where left side's not equal to right side, then we end up with this case right here. Okay? The vector, or sorry, the line and the plane are inconsistent. Okay? And that means that the line and plane are parallel to each other. And that's your conclusion. So therefore, line and plane are parallel. No solution. All right. And I have one more to finish off in the next video.
With following student dials.